Welcome back. In this lecture, we will look at certain aspects of electrodeposition, especially certain mechanisms that are associated with growth following nucleation. So the phenomena is fairly complex for multiple reasons. Um, Crystal growth has been studied from the time of Oswald. There have been beautiful experiments. And in the initial stages, well, experiments were done. The way to model this was via continuum models. Okay. Later, because in those times, even the notion of atoms were debated. Later, when these debates stopped and atoms became clear, people were trying to merge the continuum models to atomistic models. So the entire phenomena can be quite complicated. So the way research is done in this field is you make some measurements, and then there are some models and connecting the experimental measurements to phenomenological models gives you a clue on what is the dominant mechanism. We'll try to illustrate as we progress in this lecture. So, as I said, in the previous lectures, we have um, discussed the variety of physicochemical processes that are involved in electrodeposition. Specifically, we also talked about critical nuclei and the Gibbs free energy changes during nucleation and growth. So while the previous lectures, at least the last two lectures, have been focused on nucleation, we will talk more about growth in this lecture. So there are ways to think about growth. In one model, we imagine that the growth occurs independently in different nuclei. One may imagine that the different nuclei are separated from each other. That is, they are not interacting directly. So each nucleus can grow independently of the other nuclei. So they are far from each other. Each of the nuclei are far from each other. And the overall current is the sum of all the currents due to individual nuclei. So that is one way of thinking about the growth phenomena. So we think in terms of limits. This is one limit, which is probably easier to model. In the other other limit, the growing nucleus post nucleation, the growing crystal is interacting. So it can also be that in the initial stages of growth, there is not much interaction. And as the growth progresses, the interactions kick in. So in one of the models, we consider the growth at constant potential. And this constant O potential is such that the constant potential is such that the O potential is not that much. So the rate is sufficiently slow, and the concentration of the species that are involved in crystal growth do not change significantly. Okay, so this is the concentration. Let's say there is an electrode over which electrodeposition is occurring. We are talking about concentration of the species, relevant species, adjacent to the electrode. That will also control, let's say, free adatom concentration on the electrode. This is not changing with time. This is a reasonable assumption when the rate is sufficiently slow. Therefore, the transport from the bulk of the electrolyte to the surface is much faster than the crystal growth rate. Therefore, CS is not changing with time. So in a simplistic model, we can think of these crystal growth as a two-dimensional cylinder th- th- uh, that is growing. Okay, so for example, here you have a two-dimensional growth, that is, the adatom comes and attaches itself to these regions. So there is no three-dimensional growth, that is, an adatom does not attach itself to the top of this cluster, but these adatoms are getting attached to these lateral regions. So instead of considering a complicated structure, you can consider a two-dimensional cylinder of a particular height. This height is associated with the atom thickness. So we are imagining a monolayer thickness of a crystal that is growing, and the structure is approximated as a 2D cylinder. So from here, you are thinking about the mass changes in a particular crystal that is going post nucleation. You can consider decompose the mass into mass as density times volume. These are all approximation because we are in the borderline in a regime where continuum mechanics is barely applicable. Okay, we are just considering a small cluster of atoms. So to consider that cluster to have a constant density is a stretch, but these are some useful approximation that gives you some insight, especially when you compare the models with experiments. So the you can decompose this term as an area term times dr by dt. So the area of this cylinder is 2 pi h. H is the height times r, that gives you the area. And in the along this periphery of the cylinder, crystal growth is occurring. The rate of change of radius with respect to time is given by this quantity. Then once you know the current density associated with a particular growing crystal, you can multiply that by the area to give the current, and using the Faraday's law, you can get the moles and you can multiply that by molecular weight. So these are all fairly simple manipulations. So from such an expression, we can get an expression for dr by dt. So what is the boundary condition? So we always need to have a nucleus for the crystal to grow, right? So you cannot have r equal to 0 at time t equal to 0. But as an approximation, we consider r to be approximately equal to 0, okay? Because let's say that the size of the growing crystal is much larger than the nucleus. So we can approximate r to be 0 at time t equal to 0. With this, you can solve this fairly simple differential equation. And what you see is that r scales linearly with respect to time. Linearly with time. So for a 2D growth, we can simplify and get an expression. So IS is current density times the area. So we see that IS scales linearly with time. In contrast to this 2D growth, we can assume a 3D growth. So instead of a cylinder, you can have something like an hemispherical object that is growing and so on. The boundary conditions and differential equations are slightly more complex, but it is not too complex. But the sum and substance of this kind of a model is that IS is proportional to t square. In a 2D growth, it is proportional t. Here IS is proportional to t square. So what is that we should be noticing is that it is very difficult to observe whether the growth is 2D or 3D. However, when we measure IS, okay, that is a quantity that can be measured, the overall current, okay, so which is just, let's say, number of nucleus times current due to each growing crystallite. So that can be measured. And you can, of course, measure time. When you plot total current with respect to time, depending upon the way IS scales with T, whether if IS scales linearly with T, then we get a clue that the underlying mechanism is two-dimensional nature. However, if IS scales at 2T square, okay, so then we can get a clue that the underlying mechanism is three-dimensional in nature. So that's the way research is done, especially in the early stages of research in this area, because in situ measurements were very hard, and then model building from atomistics was also very hard. So as opposed to kinetically control growth, that is when the rate is very slow, you can consider another model where the O potential is much larger, the surface reaction rate is much faster, because of which the concentration of the species adjacent to the electrode is low. Okay, so it is so the transport from the bulk, this species, the transport of this species from the bulk of the electrolyte to regions adjacent to the electrolyte, that transport mechanism is controlling. That is slower compared to the crystal growth rate. So in this limit, you can consider a particular limit where CS is 0. Okay, so this helps in setting up the bound differential equation and solving it. And within the pseudo steady state approximation, for a three-dimensional hemispherical growth, we can get an expression. The main thing to notice is that whenever IS scales as square root of T, this T to the power of 0.5 will show up often in a variety of contexts. In this context of crystal growth, we are discussing. However, in battery research and supercapacitor discharge times and so on, this T to the power of half will show up. Whenever such a scaling occurs, you should get an idea that some aspect of diffusion is important. Okay, so square root of T is an important term that comes when diffusion plays an important role. People who have, let's say, chemical engineers or materials engineers who have looked at, let's say, mass transfer, you might have looked at ballistic phenomena as well as diffusive phenomena. So here, square root of T dependence gives a clue that diffusion plays an important role. Moving on, in all the previous slides, in the last few slides, we looked at instantaneous nucleation. That is, the nucleation is well separated from growth phenomena. So in this case, the total surface current is the current from a single nucleus. All these models are associated with current due to a single nucleus. The total current can be obtained via multiplying the current from a single nucleus times the number of nuclei on the electrode surface. So how to estimate this? We have discussed this in some previous lectures. From the nucleation rate and the time, we can get an idea of the number of nuclei and so on. So here, the nucleation is well separated from growth. This regime is referred to as instantaneous nucleation. Nucleation is separated from growth. As opposed to this, we talk about a regime wherein there is progressive nucleation. In this case, as the growth occurs from already um, nucleated species, the nucleation continues to occur. Okay, so um, so this is very important when we consider, let's say, monodispersed um, crystal growth. Okay, so if you want to have fairly monodispersed growth, you typically tend to have systems wherein nucleation is separated from growth. This is um, in these systems, the chances of getting monodispersed distribution, okay, the size distribution is fairly monodispersed. As opposed to this, you can have a system wherein nucleation continues to occur during growth. So the formulae are different. So these are the expressions for instantaneous nucleation. These are the expressions for progressive nucleation. For 2D growth, 3D growth, you can derive expressions. These are given in your textbook. These expressions are for uh, when the O potential is low, the transport is not controlling. These expressions are for um, wherein transport is controlling. We have not attempted to derive any of these expressions. For further details, you can look at the references quoted in the textbook. So moving on, we look at another scenario where the growing crystals are interacting with each other. That is, in all these cases, you can think that the nuclei are far away from each other. They were not interacting. As the crystal growth occurs, each crystal is not interacting with the other crystal. But as opposed to this, the crystals will interact. And what is important to notice is that in all these expression, there was no exponential term. But here, there is, this term is similar to the terms that we showed here. But in addition to that, this term is multiplied by an exponential term. There is a negative sign here, and time is here. So this exponential term, for example, at early stages of growth, this exponential term can be um, represented as a series expansion, and you can drop many terms, and you can get a simplified expression. But what is important to notice is that um, the exponential term will start kicking in as t becomes larger. Both in instantaneous nucleation and progressive nucleation, you can derive expressions where the growing crystals interact with each other. Okay, so in both instantaneous and progressive nucleation, there is an exponential term. So what is the consequence? The consequence is that in the early stages of crystal growth, early stages of electrodeposition, current is more or less linearly increasing. Okay, so this is the plot for instantaneous nucleation. This is the plot for progressive nucleation. But after a certain time, this exponential term kicks in and the current starts decreasing. So again, the approach to way to understand the system is that you do two things. One is there are a set of measurements that are made. Okay? And then the other aspect is that you build some models to get some expressions. Then you correlate the things that are measured, in this case, let's say current versus time, with the different models available to you. Let's say instantaneous nucleation, progressive nucleation without interaction, then instantaneous and progressive nucleation with interaction. Then using these comparison, you get to the underlying mechanism. Okay. Then in the contemporary research, let's say in the last 10, 15 years, it has become quite possible to undertake growth studies, simulations from atomistic model. This has also given a lot of insight into the mechanisms that are responsible for crystal growth um, and electrodeposition. In the next lecture, we will look at certain aspects of deposit morphology and how additives are important in controlling the deposit morphologies. This will be a bit descriptive in nature, but these are extremely important topics in industrial application, okay, of electrodeposition. We'll look at these topics in the next lecture. Thank you.